Okay. So last week we talked about the need for understanding some radiative transfer, and I'm just going to go through where we got. We looked at angular moments of the intensity. We managed even to figure out what an atmosphere in radiative equilibrium looks like and how we might solve these things for a gray atmosphere, etc., etc. And we ended up looking at what happens for optical depth around unity, so between 0 and 3 or 4. We ended up looking at what this solution to the transfer equation, namely the lambda operating on the source function. In this case, we've just put in some analytic source functions. Yeah, I don't know why it's not working on the screen. We have looked at those things, and today I think we're going to look a little bit deeper into how things like spectral lines are formed, as well as just any old, frequency. So this applies to the numerical solutions are just shown for a given source function without any information on intensity or anything. So it's just basically you might consider it one frequency, or you might consider it, but because we're specifying the source function, it doesn't really matter what we use there. But now, of course, one of the things about spectroscopy is the use of spectral lines, which is the most important thing. I mean, if you think about it, if the natural width of these lines had been a few orders of magnitude larger, we would have a hard time determining things like the speeds of things moving around in the universe. And, we know about things like dark matter and dark energy precisely because of the narrowness of these lines. And it turns out that they're narrow only because of the constants of nature that we've been given that form part of the standard model. Okay. So we're really, while these are interesting and have shed some light on how things might work. For instance, if we had a gray atmosphere, the top right panel shows us roughly what the temperature structure should, or rather the temperature structure needs to look like in order to satisfy a condition of radiative equilibrium, which is really remarkable result considering it's only like a 2 or 3 line piece of high school, algebra. So we've understood the structure of a stellar atmosphere to some degree here, at least in the radiative dominated area at the top of the atmosphere. Okay. But now we want to know about things like spectral lines. Why do we want to know about spectral lines? Again, well, as I just said, they can measure Doppler shifts, and in fact, in the business of plasma spectroscopy, the lines are probably the most interesting. They're all, as far as a lot of the dynamics in the universe is concerned, they almost look a bit like delta functions, not always, but frequently, meaning that they're narrow compared with, the typical speeds at which things go around galaxies, things orbit the sun. We're moving at 30 kilometers a second around the sun ourselves. That number is big compared with the sound speed at the surface of the sun, for instance. Why is that important? Well, it means that the presence of a planet around an object like our sun, if we're moving at 30 kilometers a second around it, the sun is moving at obviously the ratio of the two masses, which is very much smaller. But if we have a very narrow line, then we stand a better chance of detecting a fluctuation in that. And of course, that's how many extrasolar planets are detected. So let's have a quick look at these spectral lines then. The natural widths turn out to be on the order of about 10 to the 8 hertz, 10 to the 9 hertz in frequency. Why is that important? It's important because the line width of say a hydrogen atom on the surface of the sun is about it's going to be on the order of about 10 to the 11 hertz, something like that. So our line's natural line width really does look like a bit like a delta function as far as the sun is concerned. Not quite, but it is. And when we have a line profile from one atom in the sun, it's going to be a native profile looking like a Lorentzian, the mathematics of the decay of the spontaneous decay of an atom. You take the Fourier transform of that time dependence and you get a frequency dependence, and it's a Lorentzian shape. That's a 1 over distance from line center squared plus something, and it's very narrow, but it has quite broad wings, because in the wings of the line it goes as 1 over the in the wings of the line you don't have any it's just a 1 over distance from the line center squared, so it's algebraic fall off. Move that one. Okay, so let's look at something. We know then that if we do that was for one atom. Now we put it inside a thermal plasma, and each one of those atoms is moving relative to the center, say the center of mass of the plasma, with some fluid velocities. But it also, because we're looking at plasmas, it's hot. By definition, it has to have a broadish thermal width. And so we convolve the Lorentzian with a Maxwellian distribution, if we believe it to be Maxwellian, and we get a very nice profile called a Voigt profile, which is basically looks like a Doppler profile in the core, which is e to the minus x squared, where x is the distance in Doppler widths. That's just a typical width of the distribution of the motion of the ions that are radiating, or the atoms that are radiating. And so in the core, it's dominated by the smoothing of the by all the different atoms moving relative to one another in the Maxwell-Boltzmann distribution along the line of sight. But then as we get further away, as x increases to say 2 or 3, we start to see these 1 over x squared kind of behavior. And that's what's listed at the bottom here. So that just summarizes what I've just said at the bottom. The profile can conceptually be thought of a normalization factor times e to the minus x squared. That applies at a small at all frequencies, plus at frequencies say x greater than 3 or 4 from line center, a number called a over x squared. So this is not an approximation you would put into a computer program. It's just looking at the asymptotic behavior of x is small and then x is large. And as I said, that value of a, that's just a statement of what I said at the beginning, which is the sum of the Einstein coefficients out of a given level, which is just the decay rate of that level, divided by the width in Doppler. It's about 10 to the minus 4. So the bottom's about 10 to the 15. The top's about 10 to the 8 to 10 to the 11 or something like this. So, sorry, delta nu is about 10 to the 11. It's a small fraction of the actual jump in energy between levels J and I. It's about 10 to the minus 4 of that. So we end up with 10 to the 8 over 10 to the 12, 10 to the 11 there, and we end up with a number like that. So what this means then, what does this really correspond to? Well, the atom in the line core, if a photon is traveling where x equals 0, it's going to bump into a hell of a lot of atoms. We ignore the right-hand term because, again, this is not an equation. It's just a way of thinking of it. And that right-hand term only applies for very large frequencies, greater than 3. But it's dominated by the Doppler core. So that number is about 1 in the Doppler core. You multiply it by the cross-section, pi e squared over 4 pi epsilon naught mc. I happen to know that number because I've stared at these things for so many years. And you get the probability per unit length of making a transition. You get the absolute magnitude of phi, which when you multiply, which is the thing that you need to, you take phi, which is normalized, it's in itself, so that all photons in equal the number of photons out, and we normalize it to 1, and you end up with an absorption coefficient because of that factor I just said, and that gives you the path lengths. It gives you an absolute value of tau at line center, say. And so you can see that the optical depth in the line in that plot is very high in nu zero, but very, very much smaller. So if you remember the Eddington-Barbier relation, imagine looking at those two frequencies in the line, the dashed line on the left, you would see way down into the atmosphere because the amount of absorption is very small, the mean free path is very large, and you see way down there, and you will see, you know, stuff deep in the, say, solar photosphere because it's deep. Remember, we saw the graph of radiative equilibrium dropping with height. That means it's going to be a higher temperature than the other stuff. And so what we're seeing here is that this spectral line, if we measured one at nu zero, we would see much higher up in the atmosphere. And that number might be, for instance, an order of 10 to the 4 times more opaque. So we'd be looking really at tenuous stuff. So each spectral line spans a very large range of depths according to pressures and densities and things in the atmosphere. Okay, so that's the spectral line. All the stuff we talked about in the spring gives you the numbers that you multiply these things by quantitatively. And so the atomic physicists have done a good job in calculating AJIs and calculating collisions between things. And so we basically now have the components we need to construct a tau nu, which is, remember, the integral of the absorption coefficient along the line of sight. Okay, so in principle, we have everything for a spectral line. So now let's do the same trick we did before. These are from Rob Rutten's lecture notes from 2003, which are available online. You can look them up. And so let's just have a quick look. And what we're looking at here is a sort of a kind of representation with arrows of where photons originate and the contributions to the intensity as you go from left to right through these sort of amorphous blobs. And then the emergent intensity is shown as a function of frequency on the right. So let's look at the top left one to get started. This is a situation where the thickness of the atmosphere of this blob from left to right, that shaded area, is going to be such that essentially no photons can reach very deeply at all if you were to shine that line down onto it. Conversely, with the light coming out, if it's intrinsically radiant, say it's hot, it has a Planck function as a source function, then all the intensities come only from that little triangular area on the right side of that thing, that shaded top left thing. And then what you see is even if you have a strong spectral line, if this thing is at one temperature, you see a uniform distribution of intensity. You don't see any line at all. And that's because at each point, you're looking down to optical depth 1. And even if optical depth 1 doesn't reach the left-hand boundary, and it's just the top layer where the temperature is all the same, you see the same source function everywhere. So you basically won't see a line in that condition. That tells you something interesting. It tells you that if you have a homogeneous kind of emitting plasma where the temperature is really in thermal equilibrium everywhere and the photons are escaping from it, you can't really see the spectrum. Okay, let's go down to the next one. Now, this situation is such that we can imagine now that blob For some reason, Rob's changed the shape of it, but at all frequencies, the optical depth is less than 1, meaning that this is a thinnish layer, right? I mean, this is just like a cloud that doesn't totally absorb the light from the sun, but it's self-radiant, so we're not absorbing photons like that. And so what he's showing here is, starting from the left-hand side, we see photons on the left-hand side far from line center. So that means that we're close to where nu is 0. We'll see all the way through to the bottom of this thing. And but close to line center, we'll only see the front side of it. And so when you think about seeing, well, what is the amount of intensity we're going to see here? If you start way deep down, you only have a contribution from that across this whole layer, and that's fairly small. The contributions from line center get much bigger because you're sampling, radiation is being added up across all these depths across the whole left to right width of this thing. So what's going on is that if we now were to imagine doing an experiment where we filled a little blob with gas and we heated it up, we would first see the top panel, and then we would see the second panel. And it never, the source function, what it's showing you is that it never builds up to the point where it's equal to the source function itself inside there. So if that were a Planck function, we would measure much lower temperatures than that. So what this is saying is that because it's not completely optically thick, we don't have enough strong coupling of the radiation to the gas in order for us to see the source function of radiation there. Therefore, we're just summing up sources along the line of sight. The next one down shows you the same thing, except we have a little bit of incident radiation coming from the left-hand side. So, for instance, if you had a nebula and you look through it and you had a star behind it, you would see a little bit of a continuum there, which is notice the difference between those two, the second one down, the third one down, is that the dashed line in the second one down lies on the line equals 0. So there's no intensity there coming from a broad line width. But there is residual intensity in the next one down because we've got a star shining behind it. And if it's thin, then and the intensity is less than the source function inside there, we get an emission line. This looks exactly like the corona, okay? In principle, in the X-rays, the thermal emission, the background, the little left-hand side of that third panel down on the left would be 0. I mean, there's essentially no emission from the surface of the sun in X-rays from a 6,000 Kelvin plasma, right? It's the extreme UV limit of the Planck function. So that would essentially look like the second one down. So that's why an emission line will form. It's because the optical depth is less than 1 in both cases. And now we look at the case where actually, like something like the chromosphere, the bottom one is something that looks like the chromosphere. What do I mean by that? I mean, underneath the ultraviolet radiation, the source function is now whatever it is in the upper photosphere, in this blob of plasma. But now we're illuminating it with radiation that's actually brighter than what the source function in that region is. And again, we're just looking at given a source function. We're not solving for it yet. That'll come later. But what we see is that from deep down, we see a strong continuum in the wings. There's no line to be seen there because it's gone as e to the minus x squared plus a over x squared. So that opacity has disappeared. So in the wings, far from the line, we see just the photosphere of the sun in the continuum. So that's a Planck function at 6,000 Kelvin. Now, if we now put H alpha in there and we specify that the source function is a Planck function. We know that the chromosphere is supposed to be warmer, so the source function, it should be brighter. The line should be brighter, but in fact, what we see is it's dimmer. H alpha is only in flares and stuff is H alpha really brighter than in the core than it is in the wings. And you can say, well, why is that? Well, it's because the source function never gets to be as high as the local Planck function. It's trying to get there, but it simply can't. And we'll talk about that later. But as far as this tutorial is concerned, if the source function is lower than the Planck function in this blob, then you will get an absorption line. So that's how the absorption lines are formed in the solar upper photosphere, and how things like H alpha form in the chromosphere. So now we have a more or less complete explanation just from the solution of the transfer equation. These are just not hand waving, they're actually, pictorial representations of real solutions through that area of the di by d tau equals s minus I. And this is what they look like. And this explains why you get emission and absorption. Now let's look at a similar case where on the top right, now we've gone from very, very thick things to thinnish things, and we see a small absorption and a small emission there. But now let's look at the case where we have a situation where the optical depth is sort of in between, so that at line center it's optically thick. So in other words, photons can't penetrate deep down into this thing at line center to shoot them down at them, or they can't emerge from deep down, alternatively, but that in the wings it's optically thin. That means that in the wings, we have, say, at near zero frequencies, we see no line. All we see is the continuum down that was coming in from beneath, just like the bottom two on the left. But in the line core, we see the saturated level that we see in the top left. And so we have a flat top profile, okay? And if you were to look carefully at this thing, you would find that the sort of shapes of the line, which are, and this is again for a constant source function, right? It's a constant, that's why it's flat. So what that means is it's saturating, so that this would immediately, if you see a profile like this, you immediately know, if you knew what you can immediately say that what we're looking at is a thing which is optically thin in the continuum radiation away from the line, but it's thick in the core, and it has a constant source function. Now, if on the other hand, you have now a condition where the intensity of radiation is so bright that it's bigger than the source function, then you get the next one down. And there you get another kind of saturation where it approaches the source function at optical depth unity, because we always see the source function at optical depth unity in the line. And now we see a funny looking shape here. And you can see that line is bottomed out, but it's also broader than the one at the bottom left. At the wings, the shoulders of this thing are broader as well. So there are two characteristics when the line is optically thick, is very thick. One is the flat bottom nature of it, and it's related to the fact that the line also gets broader because the optical depth is not thin enough so that photons are escaping from the core deep down. So the photons kind of get squeezed sideways in frequency, and then you can see them. Okay, so we'll get onto that later. Again, this is very specifically for a flat source function, and we're just looking at the intensity of radiation and all the conditions. So we have, in principle, essentially almost everything we need to know to interpret a variety of different kinds of line profiles, but it's not realistic because we've assigned a flat source function to it. A flat source function means simply that either in LTE, the structure of the object is all at the same temperature, or it means that it's managed to arrange itself so that it's not in LTE, that there's a temperature structure there, but we have an isothermal region that's resulted from the energy balance of, say, a high magnetohydrodynamic calculation that mimics something that looks like it's a flat thing. So those are very special conditions which aren't usually met in astronomy and certainly not in the atmosphere of the sun. Okay. But hopefully this is a useful guide to how you see things work. So let's now look at a solar model where we actually do have a temperature changing with height. Remember, we showed a while back and that we have this top right figure here. This shows you as a function of the gray optical depth that we're assuming, it would be like a Rosland mean. That's something that's designed to represent non-gray conditions in order to do rapid calculations for stellar evolution. But you end up with a gradient in the source function, 1 plus alpha times tau, and alpha is 1.5. So we've got we don't have the case on the left there with a flat source function. That's what we just looked at. Now we have one which has got a temperature, and that's shown on the right-hand side. Okay, now there's a reason for, instead of plotting, so if we look just at the right-hand side in H and T, you can see the odd situation that we've kind of, if we flip the axes by over from as a function of temperature as a function of height, then we would see the same shape there. We would see a drop in temperature with height. All that Rob has done here is to flip those because it's going to a higher height corresponds to a higher value of the absorption coefficient. So what we want to do, so it looks a little confusing, but this is a solar thing with temperature reducing as a function of height. It's just plotted orthogonally to that. Okay. So we have whatever we have. We have a void and a continuum profile. So in the wings far away, we've got a constant number. That's the continuum, whatever the local continuum is, H minus, for instance. And then we have the line profile in the middle, centered at nu zero. Okay, so let's look at the dashed lines there and follow just the one from the top left, just underneath where it says void plus continuum. And we go downwards and we say, well, how bright is the emergent intensity? It's equal to the source function at tau equals 1. So at this particular optical depth. All right. So we have an optical depth on the right scale here. It's on the right of this void plus continuum, right just to the right of the hour. That tells us the continuum optical depth. We know that its optical depth is going down to 1 here. This is the log scale. And where tau equals 1, we go all the way to the right and we find, oh, the temperature's pretty high, right? And now we say, well, at this frequency, nu, what is the value of B nu? We come down from the right-hand side, follow the dotted line, and we say, oh, it's actually really high. So now we come along finally to the thing as a function of frequency, and we say, oh, we've got a high intensity at those 2 points where the horizontal line at the bottom left joins the solid line. Those are the continuum intensities that correspond to this point in that wavelength of the line. We can follow the same argument at nu zero. So we start at the top left, we got the dotted line in the middle, and we follow that towards the left here, and we see that it's the line center is optically thick where that 0 is on the top horizontal line on the top right. That's where the height is very high. And that we follow it down to on the x-axis tells us that the temperature is very low. It tells us that the Planck function is very low on the bottom right. And now we go all the way back to the bottom left, and we see that the line profile is an absorption line in the case where we have a gradient in the temperature versus height. So, in other words, this is a model for the solar photosphere. Solar photosphere is going to produce absorption lines. Okay? And the solar photosphere, why do I say it's a solar photosphere? Well, I've put the Planck function as being equal, its source function equal to the Planck function. Remember, we're just following our rule, which is to say that the intensity coming out is just a source function at one optical depth, the optical depth of 1. And in general, what you will find is that the densities and temperatures are such that in the photosphere, you might have 10 to the 16 particles per cubic centimeter. Corona has about 10 to the 8. What that means is the collisions are extremely rapid. And it means also that the mean free paths of the photons are very small, and both of those conspire to try and force this thing into a thermal equilibrium state. Even though we know photons are escaping, because that's the photosphere. I mean, that's what we're seeing is photon escape. That's how the sun is getting rid of all its energy. It so happens that for main sequence stars like this one, it actually is a pretty reasonable approximation. And until the 1950s or 60s, essentially all the analyses of stellar work, apart from those done of planetary nebula, which were known to be very tenuous things because they showed a lot of forbidden lines in which the densities, in order to see them at all, the densities are very low. But in stellar atmospheres, this was pretty much the name of the game until the 1950s. Okay, so we have an understanding of that now. And it really can be this easy. So what does alpha nu tell us then? And what would a measurement of this line then tell us in the sun? Well, alpha nu is proportional to the probability of absorbing a photon. That means it's the oscillator strength, the line profile. The line profile contains information on the width, the thermal width, and the non-thermal width. So we've got information here on the temperature, on the non-thermal motions, things like flows, things like shocks. And then it depends on the abundance of the element. So we've got the abundance in there as well. So what you can see is that for each individual line, that depth is determined by a whole variety of parameters. But now if we were to look at, say, 10 of them, of different elements with different weights, atomic weights, formed at slightly different heights, formed at the same height, at different abundances, different ionization fractions, suddenly we can ask the question, is this atmospheric structure compatible with that we can compute these line profiles for, given an LTE source function? Is it compatible with what we see? And if it is, what can we conclude from that? And that is basically the business of the analysis of stellar atmospheres, beginning with the work of Cecilia Payne-Koposchkin, who was the first one to really show what the equation of state combined with the populations of various things like hydrogen and helium, why the hydrogen and helium ions appear to have such weak features in the spectra. Instead of it being in abundance, it was really an effect of the equations of state, because hydrogen and helium have very high excitations compared with most of the other elements. Okay, so we know immediately. So we've got part of the way now. Remember, the goal at the very beginning of all this was to ask the question, what can we diagnose in our plasmas? Potentially, with this kind of analysis, in the photosphere alone, we might diagnose motions along the line of sight. If we have high resolution observations, the new naught will move around according to the Doppler shifts. So we can measure oscillations of the sun. We can measure wave modes propagating. We can measure downflows in granular lanes. If we can resolve these things, we can measure upflows in the interior granules. We can measure convective flows at a larger scale, supergranulation. We can get the abundances. We can get but these are all averaged over something. But we needed the radiative transfer in order to be able to do that. And it can be as easy as this. And indeed, so one could go away with a model of the sun, compute alpha nu, given the height and temperature and everything, and just throw in a few simple atoms and throw in some numbers that are characteristic of those atoms, and compute for yourself a spectrum using the Eddington-Barbier relation, or you could use a formal solver to do that. Okay. One of the questions that came up last week from Maurice was interesting concerning in spectral lines that I hadn't got to at that point, but at this point I thought I would add just a little something here about the construction of the transfer equation for spectral lines, and this will become important later when we talk about how to how to make numerical calculations for many level atoms and solve completely for I and S and the populations in one go for a given stellar atmosphere. Okay, so here's our transfer equation, conservation of energy again, at each frequency. And we have an absorption coefficient and an emission coefficient, and I've written them separately here. Because if you imagine, while alpha and J are related, and in LTE, we know in thermal equilibrium, we know di by ds is 0. So then we would have alpha times phi plus minus J times psi is 0. So we'd have a relation between alpha and J, and those are the things in the source function, remember, J over alpha. And so we would have a ratio of those two things for a light profile, which if it absorbed the same amount with probability phi as it emitted with probability psi, if those were the same function, then our source function would be independent of frequency for the line. And that is called complete redistribution. Okay, that's a word which says that independently of whether a photon, and now I'm starting to talk about photons here. So here is an algebraic formula which has continuous functions. There's nothing quantum mechanical about that one there. And we're saying is psi nu equal to phi nu. And we're going to say, let's for once just make it so that it is the same function. What does that mean? It means that if a photon's absorbed at frequency nu, the chances of it being emitted, and it's given by probability phi, the chances that it's going to be emitted at that same frequency is phi. So then if I take the ratio of those two terms to each other to describe a source function by dividing by alpha, we divide by minus alpha on the left-hand side, then we get a radiative transfer equation is di by d tau, which is equals to S minus I, and S is independent of frequency for the line. That's a huge advantage, because it means that when we add up everything that makes an alpha, once we've got the number densities in an atom, we know precisely what the source function is going to be at each frequency. However, if psi is different from phi, and it is generally, then we need to carry along with us a function of, say, phi over psi in order to be able to solve this equation. And this is where things become interesting to some people, a bit of a pain to others, but this is called partial frequency redistribution when this is not true, this question mark. And the only point I want to bring up here before we get into that, because it will become evident why that's important later in the numerical solutions, is that I'm going to now talk about this in terms of the migration of photons in space, which is di by ds. Remember, the I is essentially the Maxwell-Boltzmann distribution function, the Maxwell distribution function for photons. So I'm now just interpreting this in terms of photons. And then the easiest way to think about this, starting with people like Adams in 1970 and stuff, is that photons have a tendency to move around not only in space, but also in frequency, okay? So if we now consider something very, very simple, which is what is the probability of a photon actually escaping from the medium let's put an atom with let's put a photon in a plasma subject to these line profiles and ask the question, okay, what is the probability of a photon escaping if it was, say, in the line core? Well, if the local optical depth in the line core is very large, then the probability of it actually making it out of there is e to the minus tau, by definition of what the optical depth is. So if we now move to frequencies away from line center, where the optical depth is dropping, according to e to the minus x squared, say, then we eventually will get to the place where that number tau, e to the minus tau, is on the order of 1 or less than 1. And if it's less than 1, it says that, well, the probability of escape becomes e to the minus 1 for that frequency. Now we go to further away from line center, and it goes to a much larger probability of escape. So what it means is that the photons, if you now look at, instead of looking at this analytic approximation, we're considering particles bashing into, photons bashing into atoms with these different probabilities, then we can say that the probability that we're going to see that photon is 1 in the wings and it's 0 in the core. Now we move to a different part of the plasma where it's perhaps less opaque, and so it's closer to us. We're observing a little bit higher up. And now what that means is that this value of the frequency at which photons escape starts to get closer to line center until we get all the way to the top of the atmosphere when all of the photons escape. So what kind of consequence is this going to have here? Well, remember, I talked about the idea that in this flattening, there was some broadening here. And this is actually what we're seeing is we're seeing photons down here are not escaping from beneath this point, but they are escaping to produce a profile up here from regions of the atmosphere where it's not frequencies that are not so thick. So this is pretty obvious, I hope. So if we put in a Gaussian function here, we can evaluate an integral from x0. That should read x0. So that's where the optical depth is less than 1 somewhere in the line, because if it's higher than 1 in the core, somewhere in the line it's going to be less than 1. So we integrate those out, and these numbers scale roughly as 1 over tau, of the line center probability, 1 over the tau times the square root or something, some analytic kind of approximation you can use there. But what it means is if the line is optically thick at line center, the photons are going to emerge at a frequency which is the square root of log tau times the line width. So here we have an idea that the photons travel vast distances depending on frequencies in the line. And now you can see that psi and phi take on kind of an interesting role here, because if psi and phi are the same, then we end up with a sort of frequency independent description of what's happening, and the photons kind of are rather simply connected locally to the plasma. Whereas if psi is very different from phi, and indeed this can be the case, then the escape probability doesn't take this into account. That's just the probability of escape. But if we've got many more photons emitted, say, in the wings than we do in the core, if psi is not equal to phi, because the photons kind of remember what frequency they're at, because they haven't been collided and redistributed at all angles and at all frequencies, then we have a different kind of transfer problem. So I just wanted to, and that may have been confusing, but I'll come back to this, because these ideas of escape probabilities become essential to developing methods for numerical radiative transfer, which in which one has an iterative scheme, and you use escape probabilities roughly to tell you a solution, but then you cast your equations into a form such that you converge to the correct solution, and you use matrix algebra, and the inverses of those matrices, which can take a lot of time, become very much more easy to calculate. And so you can use like a Newton-Raphson scheme. This will hopefully become clear in the next month. Okay, just to finish up today, we've prescribed source functions, but that's not what we want. What we really have is two interacting systems. We have radiation and we have the plasma, and they're coupled through the electromagnetic radiative terms. So things like A and B in this equation tell us the rate at which photons are emitted, according to whether it's spontaneous or whether it's induced, like in a laser, or whether it's absorbed, and that's the B12 as opposed to the B21. So if we're to have dN by dt is 0, then we must, so that's the rate at which atoms move from level 1, say, to level 2. That's a 2-level atom there. So what we have, that's called the statistical equilibrium equation. So all that's saying is that, well, the plasma is living a long time. We know radiation's coming out of it, so the loss is coming out. It's also being heated. So presumably there's a balance. If it's sitting there for a while, it's not changing much on, say, a sound crossing time, then we can reasonably suppose that this condition is true. That, in other words, on average, each atom, each little black dot in there is not changing statistically very much. Each atom is changing probably all the time, according to these equations. But when you look at an ensemble of them, this describes the number of them. And you would say, well, let's fix the number to be there's 10 to the 8 of them, say, hydrogen atoms in a volume. And then you add, so the sum of N1 and N2 is then 10 to the 8. And then you use this equation here to say, well, we want to know the ratio between N1 and N2 as well. And so we'll use two equations. One is the absolute number of them, and the second one is this one, saying what's the ratio. And you can see that there's two kinds of terms here. One is the radiative term with the J bar and the A, and the other one is the C12. And now what's this? This is the collisional ones we were talking about earlier, where you have inelastic collisions that make the hydrogen atom jump from level 1 to level 2, whatever those levels are, okay? So we've got something in that equation called a J bar, and we've got an N. So we've got two types of data in there. The C12 includes an electron density as well, because the electrons move fastest. They're the ones with the charge that influence the atoms the most. And so we've got the number densities of hydrogen, the number density of electrons. It also depends on the temperatures or the distribution function that's implicit in the C12 and the C21. So we've got a bath containing the dots in that figure on the right, which are the electrons and ions. And we have another bath consisting of the wiggles, which are the photons moving around there. And, well, the photons, we know, once we know J bar, we can compute the number densities. But the trouble is we don't know what J bar is yet. But we do know that given a source function, we can solve for J bar, because J bar is nothing other than an angle and frequency average of the intensity in that transfer equation with its boundary conditions. So what we've got to do is, if we really believe it's in statistical equilibrium, we have to find a steady state, dN by dt is explicitly 0, in which we have a simultaneous solution for I, and then J, integrating J is just the angle average, remember, of I, 1 over 4 pi integral I nu d omega. And then we've got to make it so that it's compatible with that. So what we have is, we have, and this equation for I is actually integro differential, because we have to solve for S. if we have phi and j equal here, turns out that the S nu is just a function of the number densities. Doesn't depend on frequency. So we can actually imagine putting a little bracket around that S on the transfer equation, two separate equations, we've got to solve something, and that's actually some functional of n. Now we have two equations, which one of which is just a simple algebraic equation for n, and the other one is a functional of n that we need to solve. And the whole business of non-LTE radiative transfer is making these two things the same. And you can see that if I've eliminated the variable j bar from the first equation using a functional n that I put in there, so that I get a j bar, which is some functional of the number densities in here, then I have two equations. Actually, the top equation is one equation, but we have an equation of state, and a total number density for the hydrogen atoms. And then we have a functional equation down here. So we've got two equations at the top, and we've got an equation at the bottom. And we can expect to solve for the I nu as a function of the n's, and the n's as a function of I nu in some iterative fashion. It's not guaranteed, because if you look at this, we've got the physics of S nu is actually, quite complicated. I mean, we've got emission of photons at one frequency. Maybe they emit at a different frequency, like in this picture here. And we've got to take into account that physics. We haven't discussed that at all. So this is not a straightforward thing, but this is what separates people that do radiative transfer and non-LTE from people that do coronal physics, is these two basic equations plus the conservation equation for number density is what we're looking to solve. 5 minutes left. Just to show you the bits and pieces, then explicitly what this looks like. I've now replaced all the coefficients by just adding them up. So we have the radiation field at the top and the collisions. This is the mean radiation impacting. It can be anisotropic, but this is the mean value telling you a number of photons making the jumps. The spontaneous emission is A21. And then A and B are related to each other. B12 is related to B21 by thermodynamics. And we have cis equilibrium. We have the definitions of the J. For a plane parallel atmosphere, it looks like this, where that's a cos theta, the usual cos theta. We have J bar there. Once we've integrated that, as I said, to get the level populations, we need the radiation field. To get the radiation field, we need the populations. And this source function, ultimately, if you have complete redistribution so that phi nu and psi nu are the same, this is just a rather simple expression for this thing. And we can plug this in directly for S nu with a phi nu in it into this equation here. And now we see what the nature of that thing is. It's locally now N1 over N2, and these are local. The non-local coupling comes in here because we have to solve this. This is remember, this is an integral. This is the local radiation field. This is its change. So we have to solve this. This is the non-local part, and so we end up with the nuts and bolts that joining the plasma to the radiation end up looking something like this. When we have a multi-level atom, we have a matrix instead of an equation here like this. In fact, we have a matrix here as well. It's just 1, 1, and then P12 and P21 in some form. 1, 1 means sum up the populations of a vector with two components, and then this one tells you the ratio of them in statistical equilibrium. So that's all we really need. And if we now look at this two-level atom, it turns out, rather interestingly, that if we eliminate for, if we now have a parameter that measures how strongly coupled the collisions are to the radiation, so how strongly coupled are the particles, the C21s, to the radiation, the A21s, this is the escape part where it escapes locally, maybe it gets absorbed again, etc. This is a measure of how strongly the collisions couple to the radiation field. If this number is 1, it means that the radiation is irrelevant. If this number is small, it means that the radiation dominates. And it is generally very small if we take just this as being in the infrared part of the spectrum, then we end up with a thing that looks like very small. So what we see is the source function is determined by a small amount of collisions locally, but by a lot of radiation non-locally. This is the problem, okay? Non-local conditions. And this is generally the case, again, because of, this is just these are all just dependent on constants of nature, like epsilon naught, the electron charge, H bar, H is here with the e to minus H nu. Okay, so quantum mechanics is involved. In the Wien limit, it's really not. So this is just constants of nature telling us this. And in a case like the sun, this is proportional to the density. So this is not just one number. It depends on the density. So deep down, this number C21 can be quite big, etc., etc. So you have to take all this variation into account. But what we have here then is the beginnings of the looking at what I was saying, which is this iterative cycle at which you might be able to try to solve this problem. This one here is the statistical equilibrium equation solution. It turns out that you can write it exactly like this. The source function is linear in its own radiation field, okay? That's just this set of equations here, solving, and these, and the conservation equation. Algebraically, it comes out looking like that. So, but we know that given an S, the transfer equation gives us, and the boundary conditions gives us the J that we need. So we saw earlier, this is just this J equals lambda S that we had before, right? And we were looking at the effects of the slope and looking at all that. So this is exactly the same thing. And now this is the appropriate integral operator. So now I just stuff in, instead of J bar there, I stuff in SL there. And again, SL is just this ratio of populations. What I get is now an equation that looks like this. We've got a small amount of coupling to the local collisions. We've got a large amount of coupling to the mean radiation field. But this radiation field is an integral equation over space of this thing, the line source function. And so you can imagine this, if we can get a guess for SL here, we might get a new version there. And then we would end up with a way to iterate, perhaps, to get this thing to be solved so that this doesn't change when we put it back in there. There we have a solution to the whole problem suddenly. The literal implementation of that is called lambda iteration, and it's known not to work. I mean, you can go back and look at books by Mihalis and other people all the way through back to the 60s, actually. And that's because information is propagated one photon mean-free path at a time. At least that's the interpretation. Instead, we have to do something a little bit cleverer with this. And this is where things like escape probabilities come in. And you can imagine, this is integral over frequency and angle. You can imagine, for instance, saying, well, if the core is optically thick, they don't contribute anything to this integral. So I'm going to, if it's not in the core, I'm going to set it to 0. So all you got to do is say, well, what's in the core? How optically thick is it? And then you compute the frequency at which photons escape, and then you add those into this lambda bar, and you ignore all the core photons. And then that might work. And so then you would compute this thing, and indeed that does work, but it's not the most efficient way to do it, we found. That was a development of something called the core saturation method. For obvious reasons, you saturate the core, so you just pull those straight out. You don't include those in these integrals here, right? You just say, I'm not going to include those frequencies. I'm just going to include. So what I'm doing is setting basically a Heaviside function on that, and we just go from some frequency where they're escaping to infinity. We compute that, and we use that instead of the J in here, and we have this solution now. And now you can see how very simple it is. We've eliminated all the local absorptions and emissions in the core, and now we're just looking at the transport of photons around, because we don't care about the ones that don't transport. That's not what we're interested in. We have to deal with the transfer equation, and it's the difference between the source function and the other one that counts. So that's, I think, where we should end. Oh yeah, it's 11 o'clock already. So I hope I've given you some. It's a bit messy because this is not obviously fitting with the rest of it algebraically, but I felt like I had to introduce the physics a little bit, because we have to talk about photons and frequency and space. And finally, we got there with that. So next time, we'll have a look at the nature of those solutions and explain why the calcium line looks like this. All right, Ben, you still there?
Yeah.
Oh, man, he's a stalwart. Thank you so much. Any comments or questions on any of this?